Hello students, today we will discuss electric field on axis of a charged ring. On its axis, let this be the charged ring. It has plus q charge distributed throughout on its boundary. There is a plus q charge distributed throughout, and this is center of the ring. Let r be the radius of this ring, capital R. Let point P be at axis of the ring at a distance x from the center of the ring. We have to calculate net electric field, and this person is this charge is a large amount of charge. It is not a case of point charge, so Coulomb's law won't help us here. Instead, we have to use a technique of integration to calculate the net electric field. Now, for integration, you always know the process. We cut a small element dq. Let us cut a dq element here consisting of charge dq here. Let it be at a distance r from this point. So now dq will behave as a point charge. It is a very small element, so having small charge. So Coulomb's law can help us here. Since we always assume a positive charge here, so because of this dq, electric field will be in this direction, and it will be a very small electric field because the charge is very small, dE, and it is valued by Coulomb's law. Electric field by definition has a formula: the source charge dq constant k times dq upon distance is r square, k dq upon r square. Now, corresponding to this dq element, there is always opposite element dq, same distance radii r. It is distance is also r. Why r? Because you know what, this ring, it is actually like this. This is the ring, this is center, and this is, it is actually like this. So if you see, every point is at a same distance from this. If this is the point P, if this is the point P, so every point on this surface is at an equal distance from this point, if you see. So this distance is also r. Now, you know what, if I extend this line like this, because of this dq element, there will be electric field in this direction, dE, again dE, same distance, again dE. Now if you see these two triangles, if this angle is theta, this angle is theta, vertically opposite angle is this angle is also theta. Now these two triangles are x, same sides, though these are congruent triangles, so this angle is also theta. Now this dE element, we can do rectangular components in the direction of theta. They'll always come as cos component, dE cos theta. Perpendicular to it comes dE sin theta. For this dE, again this is theta, so this is vertically opposite angle, this is theta. This dE, it is cos component, again here dE cos theta in the direction of theta, dE cos theta. Perpendicular to it is dE sin theta. If you observe carefully, their sine components cancel each other. dE sin theta and dE sin theta cancel each other, and it's true for every point on this charged ring. For every, if you cut any dq element any wire, there will always be an opposite element for which the sine components will cancel each other, and net effect is total. This dE cos component in the direction of, in this direction there is dE cos component, total electric field will always come in this direction. If you see it here, for this element there is opposite element, this, their sine components will cancel, and cos components will add up. So net electric field total is nothing but summation of these d cos components. So to calculate, and if we add them all together, what we always do integration. So net effect net electric field is always the integral of this d cos theta. So it is dE is k dq upon r square cos theta. Also, if you see this cos theta, theta is same for every point, so cos theta is constant. K is constant. Constants always come out of the integration. K comes out. Cos theta constant comes out. And this R is a constant. It comes out. Since R is same throughout, R doesn't change. For this point R, this point same R for every point. Integral in integration we have dq. So it is k cos theta upon r. So you know integral of dq is nothing but q, total charge. Now we can't put it like this. We have to put the value of cos theta. Cos theta in this triangle, if you see, it is nothing but base upon hypotenuse. Base is x, hypotenuse is r. So it is nothing but k x upon r cube into q. So it is kqx upon r cube. If you want, you can put the value instead of this r. This r is nothing, it is the hypotenuse of this triangle, so it is r square plus x square. We can put the value of r, so electric field will be nothing but kqx upon, instead of r we can write r square plus x square. It is r square plus x square cube. So it is nothing but kqx. Rule, instead of rule we can try it 1 by 2. So it is r square plus x square power 1 by 3 by 2. So this is the net electric field. Now we can take two cases. If we have to calculate the electric field at the center of the ring, so for center this x will become 0. So for x equal to 0, for center of the ring x will be 0. So instead of x we write 0, this becomes 0, so electric field is 0. It means at the center of this charge ring there is no electric field. You can also visualize it. See, if we have a point on the center, if we charge it at the center, so all these electric fields will cancel each other. For this opposite element, this electric field will cancel it. So it comes to our mind that electric field will be 0. Now there is another case. If this x is very greater than, if x is very greater than r, then the radius of this ring, that means it is like this. If this is the ring, this is r and point is here, so at that point of time this x is very large than this r. In that case this r square can be neglected, so r square has no effect, and this will become x square power 3 by 2. 2 and 2 cancels, x cube, it becomes kqx upon x cube. It just becomes kqx upon x square into x. X cancels, which is kq upon x square, which is the formula for point charge. So in that very case it will behave like a point charge. When will it behave like a point charge? If this x distance of the point is very large, then the radius of the ring, and for center of the ring electric field is 0. Thanks.